Secondly, what's the dispersion of the data? What do I mean by that? The dispersion of the data is describing how much variation there is. Right? So I can use the term dispersion and multivariate variance in the same way. They're interchangeable. Right? So if I've got two groups, say males and females, do I have the same variation of them in the males as I do in the females? I might be interested in something like that. And then the correlation structure is the third thing that we've learned about now. What's the shape of the cloud of our points in our multivariate space? Right? If there is some sort of structure going on there, what's responsible for it? Which are the variables that are responsible for it? If there is structure there, can I then use that somehow to reduce dimensionality? Because you can imagine, if I've got two variables and they're highly correlated with one another, they're kind of redundant, right? Basically telling you the same information. Right? We're gonna use that to try and reduce dimensionality. All right, so this is the same sort of thing here. This is Sparrow data. You'll find this in the Manley book. Right? And we have basically some morphometrics, some data about each sparrow's size, and that was their alar extent, and which I think was the wing length and the total length of the sparrow. So they sit all in a two-dimensional space here, these two variables. But also there's a third variable, and that's whether or not they died or survived. Right? So the question of interest would be, okay, is there a relationship here between the variables? Well, clearly there is. As total length gets bigger, so does this alar extent. Right? And secondly, is there a difference in the birds that survived relative to the ones that died? Right? And how would you describe that if there was a difference? What would you say? Can you see any patterns? Yeah? So this is just a simple two-dimensional example. So we can just plot the data.
There's a linear correlation between them.
Yes, so there's very clearly a correlation between length and alar extent, right? As one goes up, the other goes up. Is it the same for both of them?
Yeah.
Yeah, pretty much, right? And whether or not they died or survived, they both have this positive correlation, I think.
And how can we distinguish between them?
Well, the blacks are the ones that survived, and the blues are the ones that died.
No, the relation between them.
Between what specifically?
Like the sparrows which have died and survived.
Right, so I would look at, so the ones that died, just look at the blue points, or the white circles, right? Look at the correlation there of just those points. And you can see as just using the blue points, as one variable goes up, the other one goes up. And then we do the same thing with the black points. Yeah. And once again, we can see that there's a correlation as one goes up, the other one goes up. Right? So, but we need to talk about other things. Is there roughly the same sort of spread in the data? It's roughly the same, but I would say the big thing is the mean, maybe, right? The ones that died probably are a little bit smaller on average, right, than the ones that survived. The ones that survived, there's a lot of blue up here, right, in this region here, and they're the ones with big total lengths and big alar extents. Okay, whereas there's a higher proportion of deaths amongst the smaller birds. So you can see what we've just done is try to look at those three things: the location, the covariance, or the correlation, and the spread of the data, the dispersion, right, to try and characterize what's going on. Okay, so that's pretty much the lecture. Oh, not quite. So this is a scatter plot, right, for two variables, right? If you've got lots of variables, but not too many, you can do something called a draftsman's plot. And this is very useful, actually. This is basically just like a covariance matrix, but instead of just giving you actually telling you, hey, this is the variance and the covariance, you actually plot the data for every pair of variables. So a draftsman's plot is a bivariate scatter plot for every pair of variables arranged in a matrix. So it looks like this, something like this. So this is Fisher's iris data. It has 4 different variables in it, right? The draftsman's plot is going to look at the relationship between these two variables. The relationship between sepal length and petal length is here. Sepal width and petal length is here, Right? So this is just like the covariance matrix, right? But in graphical form. Right? So remember the covariance matrix has the variance down here and then how they covary. Right? So these two variables are very correlated, right? So you would know that the covariance matrix would have, well, you'd have the variance of sepal length and pedal length and these elements here, and this would be the covariance between the two, and that would be some big positive number. Right? So this is just, you know, a graphical form of the covariance matrix, and it actually contains more information because it's not just describing the linearity, but obviously it's hard to look at. What we've got is a one-number summary, basically, of this data with our covariance matrix. Right? But so this is a very useful tool if you don't have too many variables. Right? You can actually start to delve and work out what's going on. This data set is very famous because it's what Sir Ronald Fisher used to introduce something called this linear discriminant analysis, which was, he was saying, can I find an access through the data that would separate these groups through my data cloud, that would separate these groups really well, axes through the data. And if you look at any single variable, or even every single pair of variables, you can discriminate them pretty well, but not very well. But if you use them in combination, it turns out you can discriminate them very, very well. Okay, so health data now is a far bigger covariance, far bigger Draftsman's plot. We've got 1, 2, 3, 4, 5, 6, 7, 8 different variables now. So we end up with an 8x8 matrix of plots, right? And you can start to see, well, yeah, you could probably get into this. And if you've got if you've colored things by, this is just obesity. If they're obese, you code them as a 1. If they're not, you code them as a blue. So you can get some idea of patterns here as well, right? But much more than this, you start to run into some problems, and it's hard to see. Right? And it would be a bit of a nightmare to summarize this to somebody, wouldn't it? There's a lot going on. Okay, so I have talked enough. Now is the time to start practical 1. Basically, we'll do practical 1 until lunchtime. What time do you guys want to do lunch? 12? Say midday? Take an hour off? Okay, so come back.